Welcome back to Code Wonka channel. Today we will be solving first missing positive problem. Let's go over the question. Given an unsorted integer array nums, return the smallest positive integer that is not present in nums. You must implement an algorithm that runs in O of n time and uses O of 1 space. Let's look at example 1 where nums is 1, 2, 0. Output is 3 because the first integer missing from range 1 to 3 is integer 3. Let's look at some example test cases and make some observations to come up with an intuition to solve the problem. With test case 1, we can draw the observation that if the array is sorted, then finding the first missing positive integer is easy doing a linear search. By looking at test case 2, we can observe that when all integers between range 1 to length of nums are present and the array is sorted, then we can say that the correct index of the element nums of I will be nums of I minus 1. For example, element 1 is at index 0. So nums of I is at index nums of I minus 1. With test case 3 and 4, we can draw the observation that all the elements out of range of 1 to length of nums in the array does not matter as they don't contribute to the output. So we can ignore these elements. Looking at all the 4 test cases, we can say that no matter what the element in the array are, the output will always be between the range 1 to length of nums. From the observations, we can come up with these approaches intuitively. The first approach is a brute force approach where we use 2 nested loops. For each index, we check if other indices have the correct element present. The time complexity of this approach is O of n square and space is O of 1. The second approach would be by using sorting. We sort the array and loop through the sorted array to perform the linear search to find the first missing element in the array. The time complexity is n log n and space is O of n. The third approach would be by using hash set. We store all the elements of the array in the hash set. We loop through 1 to length of nums and return the first element that is not present in the hash set. The time complexity would be O of n and space will be O of n. None of these approaches have the time complexity as O of n and space as O of 1. So next, let's look at the intuition to come up with an approach of time complexity O of n and space as O of 1. Looking at this example test case where the expected output is 2 and looking at the observations we made, we can come up with this intuition where the correct index of positive integer nums of I will be nums of I minus 1, given that nums of I value is within range of 1 to length of nums. If an element of nums is a positive integer in range from 1 to length of nums and is not in correct index, then put it in its correct index by a swap operation. Let's visualize the solution we discussed using the same example test case. We start by initializing the ith pointer to 0. Let's see if nums of I is within range 1 to 4. Yes, it is. Is nums of I in its correct index nums of I minus 1? No, it isn't. So now we will place the ith element, which is 3, in its correct index, which is 2, by a swap operation. After swapping, we again check the same conditions. Is nums of I within range 1 to 4? No, it is not. So now we increment the ith pointer. We again check the same conditions. Nums of I is within the range but not at its correct index. So now we will place it in its correct index by a swap operation. After swapping, we again check the same conditions. Nums of I is within the valid output range but not in its correct index. So we'll put it in its correct index by swapping. Now nums of I is not within the valid output range, so we will increment the ith pointer. Now nums of I is within the valid range and at its correct index, so we do no operation and increment the ith pointer. Nums of I is within valid range and at its correct index. So now we do no operation. Because we reached end of the array, so now we will do a second pass at nums array to identify the first index which does not have the correct element in its place. In this case it's index 1 because it has element 5 minus 5 instead of element 2. So now we will return index plus 1 as the output, which will be 2. Let's visualize the same solution but with a test case that has duplicates. In this test case we have duplicate element 1 and the expected output is 3. We start by initializing the ith pointer to index 0. Current element is within the valid output range but not at its correct index. So we put the current element at its correct index using the swap operation. Now the current element is within the valid range and at its correct index, so we increment the ith pointer. Current element is within valid output range and at its correct index, so we do nothing and increment the ith pointer. The current element is within the valid range but not at its correct index, so ideally we would want to swap it at its right index, but we can't because we already have a duplicate element at its right index, so we do nothing. Now we do a second pass to identify the first index which does not have the right element at its place, that is index 2. So now we return index plus 1 which is 3. Let's code the solution. We initialize I to 0 and n to length of nums. Then we write a while loop with terminating condition as I less than n. We determine the correct index of the current element. Then we write a if block with the condition to determine if the current element is within the valid output range and the current index does not have the same element as the current element. This tells us that the current element is not at its correct index and also helps in handling the duplicates. If this condition is true, then we put the current element at its right index using swap operation. Else the current element is either out of range or already at its correct index. We increment I. Then we write a for loop to identify the first index which does not have the correct element at its place. If we find it, then we return I plus 1. Else at the end of for loop, we return n plus 1. In the code, we have this while loop whose time complexity is O of n. Then we have this for block whose time complexity is O of n. So the overall time complexity of the code is O of n. The total space is O of 1. If this video helped in learning, then please like, subscribe and share. Leave your feedback in comment section. Thank you for watching this video and stay tuned.